Hello class, welcome to lesson 10.1, which is all about square root functions. By the end of this lesson, you should be able to graph and analyze dilations of radical functions, and you should be able to graph and analyze reflections and translations of radical functions. So, first let's talk about what a square root function looks like. We have the parent function here is the square root of x. Last chapter, our parent function was x squared. Okay, so we're doing the opposite of x squared. We're doing the square root of x squared now. So this graph is also curved. Our domain and our range for the standard square root of x is greater or equal to 0 and y is greater than or equal to 0. Some quick vocab. If I gave you the square root of 3x minus 2, the square root symbol, another word for that is radical. Okay, so you'll hear me call it a radical. And then the inside portion here is called a radicand. Okay? So we have the radical, which is the symbol, and radicand is everything underneath that square root. Okay, so let's start with example 1. We want to graph the functions and state the domain and the range. So just like previously, we're going to make an xy table. So I'm going to start by doing xy. And if we are dealing with a square root, if we have an x under the square root symbol, what we're going to want to do is plug in some perfect squares. So we have x, let's see, a perfect square would be 1. If I plug in 1, I would have 4 times the square root of 1. The square root is going to be treated as an exponent, okay? So in PEMDAS, a square root falls under the e, the exponent. So we have 4 times the square root of 1. I'm going to start with that square root of 1. Square root of 1 is 1. So then I have 4 times 1. I get 4. So 1, 2, 3, 4. There's 1 dot. I'm also going to plug a 0 in. The square root of 0 is just 0. 0 times 4 is 0. So I'm going to have a dot at the origin. Let's see, what's another perfect square? 2 is not a perfect square. 3 is not a perfect square, but 4 is. The square root of 4 is 2. So then I have 4 times 2, which is 8. So I can go and I can say when x equals 4, y equals 8. And then I can kind of get my curve just like that. So that's how I'm going to graph the function. Then I want to state the domain and the range. So the domain, if we think about this, domain, we got really used to saying all real numbers last chapter, but can we take the square root of a negative number? No. So in this case, we're going to get used to saying x is greater than or equal to 0. And for our range, what y values are we looking at? I don't have anything in the negatives down here. So I'm going to say that my y is also greater than or equal to 0. Okay, so that's my domain and range. Okay, I'm going to skip part B because this video is going to get really long if I do that, but I will quickly draw it there for you so you can compare if you would like. All right, why don't you go ahead and try solving this one on your own. See which graph does it match. Hopefully you made an XY table and you figured out that letter B is the correct graph. All right, now let's talk about graphing something when we have more than just the simple square root of x, okay? So as you can see, up here we have numbers that are going to change the way our graph looks. So last chapter, if we added 2 on the end, that told us that we were moving up 2, right? Up 2 units. So this is going to have a similar effect, okay? So if I graph these, let's practice with a few, and you can maybe see the patterns that happen. So I start with y equals -2 square root of x. So I'm multiplying by a -2. So if I make an xy table and I plug in some perfect squares, so 0, 1, 4. So if I plug 0 in, I'm going to get 0 out. If I plug 1 in, the square root of 1 is 1. So -2 times the square root of 1 is -2. And then if I do -2 times the square root of 4, that's -2 times 2, or -4. So if I plot those points, 1, -2, I don't know why that switched to blue. This is going to drive me nuts. Okay, 1, -2. Okay, I'm leaving it. 4, -4. Okay. Anyways. So my graph is going to look like that. So the way this works is the 2 stretches it, but that negative flips it over the x-axis, just like it was flipping. If I said -2x squared before, you said that was flipped over x. And then it was also narrower, was what we used to say. That was terrible writing, sorry. Same idea here. That -2 flips it over x. The negative flips it over x. The 2 stretches it out and makes it, instead of this being a 1 or a -1, it becomes a -2. Instead of this being a -2, it becomes, yeah. So that's how you graph that. 2b is the same thing, but instead of -2 and -4 getting out, we would have a -4, and then also we would have, let's see, -8. Okay, so it just kind of changes that a little bit. But the domain and the range. So now my domain, I'm still only able to take a square root of a negative number. So my domain is x is greater than or equal to 0. My range is y is, now we are on the other side, so I'm going to say y is less than or equal to 0. And the same thing would apply for 2b. Why don't you go ahead and take a look at this problem and see if you can figure it out. Good luck. Hopefully you ended up with letter A as your answer, that it's a vertical stretch and that it has been reflected over the x-axis. All right, example 3, we're now looking at, we don't have a number multiplying our square root, there's nothing there, but we have outside of our square root a -4. So the way that affects it, let's make an xy table again. If I plug in my perfect squares, the square root of 0 is 0. So then I have 0 minus 4, or I have -4. So I go and I plug that in and graph it. Then if I do a 1, the square root of 1 is 1. 1 minus 4 is -3. Then if I do a square root of 4, I get 2. 2 minus 4 is -2. So then 4, -2. So you can see that my graph looks like that. All that happened was this -4, just like before in the last chapter, it moves the whole graph down 4 units. Okay, now let's look at 3b. What if the +3 is inside the radical? Okay, it's underneath that radical. Let's do an xy table, and we'll go through and we'll do the domain and range for both. So if I plug in my perfect squares, the square root, or actually no, I want to think about this for a second. If I plug 0 in, I'd have the square root of 0 plus 3, or the square root of 3. Is that a nice number? No. So what I'm going to do is I'm going to plug in some nice numbers. How would I get to the square root of 0? What plus 3 gives me a square root of 0? If I plug in negative 3 in, I would have negative 3 plus 3. That's 0. The square root of 0 is 0. So that's how I would get to square root of 0. How would I get to a square root of 1 if what do I have to add to 3 in order to get to a square root of 1? I would need to do a negative 2, right? Because negative 2 plus 3 gives me 1. And the square root of 1 is 1. So then I can go negative 2, 1. And then, let's see, what are some other numbers that I can plug in? What if I plugged, let's see, a 6 in? What if I plugged a positive 6? 6 plus 3 is 9. So then I have the square root of 9, which is 3. So then I can go all the way over to 6, 3. So that stretches out a lot. Okay? So what happened to my graph? I now have some negative x values that work, right? So I'm going to say, for my domain, I'm going to say x is greater than or equal to negative 3. If I were to plug in, if you might be wondering, how do I tell to get that negative 3? So whatever number you add inside the radical to get that square root of 0. So if I were to plug in negative 4 in, I can't take the square root of a negative 1. So I know I've gone too far and I need to choose a bigger number. Okay, so then range, I'm still at y is greater than or equal to 0. It didn't move up or down because we don't have a plus or minus outside of the radical. So then my domain for part A and my range, my domain is still x is greater than or equal to 0. My range is y is greater than or equal to, I'm all the way down at negative 4. So your range will be whatever you have added outside your radical. And your domain will be whatever you're adding or subtracting inside the radical. Why don't you go ahead and try part A on your own. Hopefully you ended up at letter D. It's a vertical translation that has been shifted 3 units up. And let's look at part B. Hopefully you ended up at letter A. All right, example 4. I'm just going to talk through this one. This is where we have the speed s of a tsunami in meters per second. It's given by the function s equals 3.1 times the square root of d, where d is the depth of the ocean water in meters. Graph the function. If a tsunami is traveling in water 26 meters deep, what is its speed? So we've already gone over graphing, so I'm going to trust you guys to graph that. And then if we're trying to figure out the 26, all you have to do is plug that in. So you take it into your calculator and you'd say square root of 26. So you'd start here, and then you would multiply by the 3.1. Okay? And when you do that, you should get 15.8 meters per second. Okay? All right, and let's look at our last example. We have example 5. We want to graph and compare to the parent function, state the domain and range. So if we quickly graph this first one, make an xy table. If I plug 0 in, I have 1/2 times the square root of 0 minus 1. Square root of 0 is 0. 0 times 1/2 is 0. So I have a 0 minus 1, or a negative 1. Okay, then if I do, let's see, another perfect square, if I do 1, the square root of 1 is 1. 1 times 1/2 is 1/2. So then I have 1/2 minus 1, or negative 1/2. And then let's do another perfect square. If I plug 4 in, I have the square root of 4 is 2 times 1/2. 1/2 times 2 is 1. 1 minus 1 is 0. So if I plot those points, 0, negative 1, 1, negative 1/2, and then I have 4, 0. So you can see this is a pretty narrow graph, right? So this graph is getting narrower because of our fraction. And then this -1 means that it started below the origin 1 unit. So then it also moved down 1 unit. So that's how we would compare to the parent function. And then our domain and range, our domain is still, it's our x value, right? And our x values are anything greater than 0. And then we have to do the range. In our range, we have anything greater than -1. Okay? So that's how you do these problems. You graph. You say, is it narrower? Is it wider? And then you simply state, does it go up or down? Does it go left and right, like it did in the last example? And then state the domain and range. So let's do that again. Let's make an XY table. If I plug 1 in, I will get 1 minus 1 under the square root. 1 minus 1. So the square root of 1 minus 1 is the square root of 0, which is 0. 0 times anything is going to give me 0. And then if I want to get another perfect square, let's see, I could look for the square root of 1. So if I plug 2 in, I have 2 minus 1 is 1. The square root of 1 is 1. And then that's times a -2. So that's where I get a -2. Another number I could look for, perfect square would be 4. So if I plug a 5 in for x, I get 5 minus 1 is 4. I get the square root of 4, which is 2. 2 times -2 is -4. So if I plot those points, I have, let's see, 2, -2, and then 5, and then -4. So you can see this graph looks much wider than the last one, right? That curve is bigger. So we're going to say it's wider. It also moved over 1. So moved right 1 unit. And the way I know that it moved right is because of the number underneath the radical. Okay? The wider comes from that -2 up front, and the negative means that it's flipped over the x-axis. I have no idea what's going on with my pen, so sorry. Then our domain and range, we have domain, we have anything for x is greater than or equal to, here's our starting value of x, we're moving that way, so 1. And our range is y is less than or equal to 0, right? We have a high point of 0, and then our graph's going down. So that's how we would do this problem. Go ahead and try this problem on your own. Good luck. Hopefully you discovered that the domain is x is greater than or equal to -4, and the range is y is greater than or equal to -1. If you have any questions at all on this lesson, please be sure to reach out to myself or some classmates for some help, and be more than happy to help. Have a great night.